In week C material, we're going to go back to what we started talking about in week 4 when it came to solving systems of equations. So remember, the inverse of a matrix can be calculated as 1 over the determinant of A times the adjoint. And the solution to a system of equations can be written as x equals A inverse times B, or x equals A left divided B in MATLAB. So we know how to do this for a 2 by 2. So now we're going to make this more expansive for any size matrix. So in order to calculate the inverse of a matrix, we need to go ahead and find the determinant. We need to find this piece right here. And remember, if that determinant equals 0, then our math blows up. 1 over 0 is infinity. And our matrix is singular and non-invertible. So remember this concept. But it makes sense mathematically. If A isn't 0, then there's no problems. We can move on. So for a 2 by 2, our determinant is that fish, A times D minus B times C. For any other size matrix, then it can be calculated using something called cofactor expansion along any row or any column. Okay, so we're going to go ahead and investigate what in the world this cofactor is. A cofactor is a sign determinant, so note it's a determinant within a determinant, of a smaller square matrix found by removing rows and columns of a matrix. So just think about any submatrix. So this would be a cofactor. This determinant of that would be a cofactor. Determinant of this would be a cofactor. So just any size smaller matrix where you remove an entire row or an entire column, that is a cofactor. And a cofactor is signed, and that sign is determined by this grid. The cofactor always has a positive sign in the upper left, and then it alternates signs going down and across. So if I want to find the cofactor for an element in a matrix, so we'll say cofactor 1, 2. So 1, this is the row, this is the column. So cofactor 1, 2 means I'm going to go ahead and remove row, I'll do it this way. I'm going to go ahead and, in fact, remove row 1, that's not a row 1, column 2. I'm going to remove those elements. I don't want it to disappear. I'm going to remove those elements. Then what I do is I take the determinant of whatever is left. 0, -4, -1, and 3. So do my little fish method in order to find the determinant of that 2 by 2. And then I modify the sign. So C1, 2 is this element right here, row 1, column 2. And that, if you notice, has a negative sign associated with it in my cofactor grid. So I change the sign. So this is the cofactor for element 1, 2. That's C1, 2. Okay, so remove the row, remove the column, calculate the determinant of the remaining values, and then adjust my sign based on my grid. That's how I find a cofactor. And it turns out to find the determinant of a matrix is we just pick a single row or a single column. It honestly does not matter, but we pick a single row and a single column in our matrix. So let me pick column 1. We find all the cofactors for the elements in that row. So for this element, I remove row 1, column 1. So C1, 1 equals positive from my grid here. Remaining elements, 6, 1, -1, 3. Then I do the cofactor of this element here. This 0 here. So C2, 1, remove the row, row 2, remove the column. My sign here is negative. Remaining elements is -3, 1, 2, 3. And then, nope. And then I find the cofactor of my remaining element. This -4 here, remove the row, remove the column. So C3, 1. It's a plus here on my grid. The remaining elements is -3, 6, 2, -1. Find the determinant of those elements. And then in order to calculate my final determinant, I take each number that I took the cofactor for, multiply it by its cofactor, and add them all together. So it would be this 1 times C1, 1, because that's the cofactor that I found for that location, plus this number times C2, 1, because that's the number I found for that location, and then plus this -4, C3, 1, because that's the number I found, that's my cofactor that I found in that position. And that's how I find the determinant. And I can do it for any row or any column in my matrix. It will still get me the same answer. So I could do it with this column. or this row. I'm going to do it with this row. So 0 times C21 plus 6 times C22 plus -1 times C23. There we go. Then I find my matrix. That's my determinant. And once again, it doesn't matter which row, which column I use, I will get the same answer. If we think about it mathematically, this is the mathematical expression for what that calculation looks like. Sorry about my dog barking in the background. But that's what it looks like mathematically. But this is the application. This is what it looks like. And that works for any size matrix. It just so happens that if you do it for a 3x3 or for a 4x4, then you will have 3x3 cofactors. And then you'll have, if you do it for a 5x5, you'll have 4x4 cofactors, which will then have 3x3 cofactors, which will then have 2x2 cofactors. And we can see the bigger the matrix, just the more of these we have to find until we get down to a 2x2. And it's just really just a bunch of 2x2s that are my cofactors at the end of the day. Okay, that's how we calculate determinant. That is our main method and works for any size matrix. For a matrix that's a 3x3, there is a shortcut. I like to call it the modified fish method, where what I can do is I can write the matrix next to itself. So take my elements, write it next to itself, and then multiply along the main diagonal. So beginning in the upper left corner. So this diagonal, this diagonal, this diagonal. Add them all together. And then I take my other diagonals. So I'll make it a different color, I'll make it purple. This diagonal, this diagonal, this diagonal. So all my red numbers are multiplied by each other and added together. All my purple numbers are multiplied by each other and added together. And then, as my fish, I take these numbers minus these numbers. That's why I call it modified fish, because it's just like a bigger version of what we do for a 2x2. Okay. This is the formal description for that, the formal formula for that. But really, it's these numbers multiplied, added together, minus these numbers multiplied, added together. Then we have properties of determinants. We're going to do an activity of these in class. So I'm not going to spend too much time on these in the video. But as we change a matrix, the determinant will change with it. So for example, if we transpose a matrix, then the determinant doesn't change. If we take the inverse of a matrix, then the determinant is also, the determinant is also inverted. If we have two rows or two columns that are the same, then my determinant equals 0. If we have a row of elements that are 0 or a column of elements that are 0, my determinant is also 0. If we multiply two matrices together, then the determinants are multiplied by together. If we have a triangle matrix, then it's just the diagonal multiplied by each other. That makes sense. And then if we do our row operations, we also can see how our determinant changes. So here's row operation 1, where we multiply by a constant. If we swap two rows, and if we replace a row by another row by adding it to another row, the elimination step. Yeah. So our determinant will change as we change our matrix in a predictable pattern. Okay, so A inverse equals 1 over the determinant A side A adjoint. Okay, that's our equation. We know how to do this part now. Now we need to find the adjoint. We need this point. And the adjoint is also found using a bunch of cofactors. So for any size matrix, the adjoint or adjunct matrix can be calculated as the transpose of the matrix of cofactors. So what we do is we find all the cofactors in the entire matrix. So if I look at this A matrix up here again, let me copy and paste it. Copy. It has 9 cofactors because it has 9 elements, where I literally just go element by element. Cofactor for this one, remove the row, remove the column, find the determinant, and change the sign. Then this one, remove row, remove column, find the determinant of the remaining elements, change the sign. This one, remove row, remove column, find the determinant of the remaining elements, change the sign if necessary. Then this one, remove the row, remove the column, find the determinant of the remaining elements, change your sign. Then this one, remove row, remove column, repeat over and over and over again until I've done all the cofactors for the entire matrix. I put them in a matrix here, so C11, C12, etc., and then I transpose it. So all my cofactors from this first row here go in this column. Okay? And that is my adjoint matrix. That's my adjoint matrix. So then I have all these pieces, and I can find the inverse. Once I have the inverse, then I can go ahead and solve my system by saying x equals A inverse times B, and it's just one simple matrix multiplication. Okay, that is the root of most of this section and most of this week. However, there is one more thing to cover, and that's Cramer's rule, which Cramer's rule is another method of solving systems of equations that only uses determinants. So, and we can solve this, we can prove this if you want, but it works. But as long as the determinant isn't equal to 0, then it turns out the solution of the system is given by these equations, where my first unknown is the determinant of A1 divided by A. The second unknown is the determinant of A2 divided by A. Where if my system equals AX is AX equals B, this A1, A2, etc. matrices is where my B vector is inserted in replacing the rows of A in a systematic manner. So for A1, it would be B in column 1, and then the rest is A. For A2, B is in my second column. It replaces the second column of A, and the rest of it is A. For A3, B is my third column, and then I keep going. So I'm replacing my columns of A one at a time in a systematic manner to find these A1, A2, A3, A4 matrices. So really, I just need to find the determinants of 4 different matrices: A1, A2, A3, A4, etc., or however many matrices, n plus 1, where n is the number of unknowns, and the determinant of A. So in order to use Cramer's rule, we calculate the determinant of A, and each determinant of AK, where A1, 2, 3, and then solve for each unknown. And that's it. So with n plus 1 determinants, we can go ahead and solve our system equations one unknown at a time.